It's absolutely wonderful to have an old friend, Mike Douglas, visiting us for the day. And he'll be telling about AI and math and theoretical physics. We'll be taking Mike out to dinner tonight. Anyone interested in coming, please get in touch with me. And we'll meet in the Bloomberg lobby around 6 p.m. Mike, take it away.
Thanks, everyone. Well, it's always a great pleasure to come back to the Institute. I have so many friends here. So I'll be, as many of been focusing on this topic of AI and how can we apply it to problems in math and physics and science. And as if you just read the newspapers, you know that this field or play with the latest models, it's advancing very rapidly to the point where there are multiple leaders in this industry saying that we should expect something that they call artificial general intelligence in the relatively near future. So what does that mean for us? Broadly, of course, but I'll focus on what does that mean for math and science research. Okay, so sorry. Slide again. You've all seen this progress. You've seen some of these applications. AI is, of course, not a new field. It's been going on since the although the ideas have a long history and have been developing steadily, the actual impact depends very much on the power of the computers that you use to implement it. And its power has been growing exponentially for many decades. It was first law and size of feature of the chip, and then correspondingly the power of the computers that you can practically build, the power of billions and roughly over a few years. And so that's a major, but not the only, but a major reason why progress continues and has been exponential and will continue for some time to be exponential. We start to see its impact in many areas. In scientific research, of course, I think the really gold standard for the possible impact is AlphaFold, protein folding, which has really revolutionized the field of structural biology. But widespread use in many fields. Of course, if you're experimentalist, you surely are using big computers, and you're probably using machine learning as this tool in your data analysis. This is I'm going to come back to this graph. This quantifies this idea of the exponential progress. This is a log scale of various measures of progress, and you see this fairly steady progression. And I'll come back to what these lines are measuring, different measures of progress, but exponential. That's up to the present day. Okay, so all that is given, but what is the impact so far been in theoretical physics research and in pure mathematics in the fields that many look at? And it has not been that large. It has not been that large. I think that many of you have surely played with it, and some of you use it. Maybe I will ask for a show of hands who has actually used it in some, to write a paper. Okay, so a few people definitely, but not the majority. And so it has uses, I'll talk, again, part of the talk will be really surveying the state of the art now. So, definitely finding patterns in data, searching for literature, searching for counter examples to conjectures, helping with coding. Many of you, again, you read the papers and you've tried it, and you see that coding is actually one of the strong points of these recent language models. To generate ideas and engage. But let's look at the ideas that people have proposed over the years and decades, because these are also not really new ideas. We should have some sort of a AI research assistant that helps us, whatever type of scientists we are, to engage, do experiments, do calculations, solve the easy problems for us and so forth. Really good mathematical and scientific search engine. I think this just starts to come as a real thing. I'll come back to this. easy to use interactive theorem proving, especially if you're a mathematician. You've heard about technologies such as Lean to verify proofs on the computer. But if you've tried to use it, you know that there's a very steep learning curve. It's not easy to use. Can a computer discover things in science and math? Later, I'll argue that there's really no serious example of that today. So why have these things not happened? Is there some kind of fundamental barrier that makes these things harder than those things, harder than what we've seen so far? And my guess is no, there's no such fundamental barrier. So still, how is this going to happen? What has to change for it to happen? So that's the kind of question that we ask in this talk, and this question I've been asking for a while. In fact, I gave this previous, rather, I'll say a more primitive version of this talk, I guess about 5 years ago, a little more here, about 30 institutes and so forth. And so, again, progress continues, and so it'll be interesting to compare what I say now with what I said then. Okay, so here are a few of the really kind of, I think, paradigms that in 2025 are working, and people, mathematicians, physicists, and so forth, do use them in write papers and so forth. And we had a program on this during the fall at the CNSA at Harvard in September, October, with many people doing this type of work and collaborating. So a lot of that discussion was based on that. So machine learning to aid in scientific computation, mathematical data science, combinatorial optimization, and interactive theorem proving. And so these are things which are survey. I don't want to try to give a lot of detail, but it's to show you the types of things people are doing now up to 2025. And again, all kind of useful if if they work with your problems, but kind of incremental. But we have this exponential progress, and we can look back and see that there are activities which you could call intellectual, where computers did go from a kind of okay to being superhuman. And of course, a very famous one is computer chess. In 1994, they were playing chess masters, and winning, losing, kind of a fair match. And 1997 was the famous DeMond. 2004, even a PC. You could get a chess engine that would beat the best chess players, not always, but very often, and very rapidly they became a superhuman. And so that's an example of computer progressing from some sort of competence and ability to a superhuman. And that phenomenon can be quantified. The kind of graph that I showed you before, we'll come back to quantify that. That leads me to really predict that we are just entering that period for research in the mathematical science. Okay, so now this is going to be a very short review of machine learning. Many of you will have seen this material. It's maybe useful to kind of crystallize it, to summarize it quickly. So machine learning, history, statistics, computer science, applied math, and so forth. And then there are some kind of canonical problems, not all of machine learning, but some very standard and widely applicable problems. Okay, and so one of the main tools are these parameterized models, such as the famous feed-forward neural networks. And from a math point of view, you can say it's a big parameterized set of functions. I have some input, say RD, big dimensional real space, some space of outputs, and then I just have a lot of parameters of these functions. And it's easy to write down these parameterized families. This will be the standard feed-forward neural network where I have an input. I have these linear transformations, matrices. I have these activation functions, some little list of nonlinear function acting on each component, like a tangent or so-called irrelevant. I just compose these into layers, and I get this very general function approximator, which I can tune the parameters and approximate a lot of functions that come up in practice, and in fact do that in a practical computational way. And then using these function approximators, well, I could learn a function. That's a very common useful class. How does a machine learn to recognize cats and dogs? Well, the input will be the image encoded in, say, a real number for each pixel intensity, or some number for each color, color trace. And then the output might be 1 if it's a cat and a -1 if it's a dog, or perhaps the probability that you think it's a cat is one component, the probability. And then the amazing thing is that that problem of recognizing and classifying images can be usefully phrased in terms of learning that function. So that's supervised learning. Self-supervised learning, in general terms, would be just a set of inputs, and you're learning the probability distribution of that set from which you've drawn your inputs. Reinforcement learning, this is then when you don't have a clear, input data set or a target that you're trying to predict, but infrequent, famously playing chess and at the end of the game, you find out on the roster that all the learning has to be based on that. And then the workhorse tool that almost all of this does characterize how well the system performs one of these tasks in terms of some explicit objective function based on, say, how well do you fit the data, maybe switch, and then you optimize that by something gradient descent or something very like it. So that's the technology, which is, of course, very efficiently implemented on GPUs and very well, cleverly written software. And then there's a lot of concepts and techniques and tricks that come along with it. The importance of data sets, having clean data, the understanding of when these functions can generalize to the models can describe things which were not in the original input data set. So partial understanding of how that happens. Why it is that models with vast number of parameters, which if you went back even 15 years ago when you asked a statistician, what do you think of these neural networks? They would have said, I actually quote, they're a crock, with so many parameters, it's just guaranteed it's going to overfit. And that was a valid argument, it just turned out to be a wrong argument. I know, so we put low boundaries on models with lots of parameters can fit. Okay, there's these techniques of training and testing sets, there's more about which models work and so forth. And then, of course, they're good for some problems. The various difficulties or flaws. One of the famous ones is that you can fit this function, some empirically given function very well, 99% accuracy, but you fail with a ansatz that has a billion parameters, and who knows what it's telling you? It's telling you perhaps nothing. So there's tools to interpret. Can you pull out something humanly understandable about such a model? Prefixure models that are easy to interpret. So that's another. Again, this is very quickly reviewing this kind of size of the field of the inputs, the types of applications now that I'll briefly review. And I'll start with machine learning for scientific computation, which is by now pretty familiar. So I'm sure you've seen many talks that talk about this in applications. So you might be trying to solve a PDE or do a Monte Carlo or this or that. And then there's, again, these ways of working with the problem to make maximal advantage of machine learning technologies, such as take out your finite elements or your basis or your spy functions, whatever, use a neural network or some sort of a machine learning model, which is very well optimized and has lots of functions. Don't do custom built solvers for your problems, but just formulate how well you've solved the problem in terms of error and objective function and minimize it by gradient descent. Then you can use all this very efficient machine learning hardware and software with relatively little work. And then finally, you tend not to have the kind of strong understanding that you have for traditional numerical analysis, and these other methods were discovered over decades. But nevertheless, you can get a lot of good results that way. Some other ideas that have been very effective in this field is this general idea of distillation. You might have a large data set of simulations, and now you can ask, well, is there some machine learning model that can, again, just reproduce some feature or just even general simulations, much simpler than actual and cheaper than doing the actual simulation of the PE. Subgrid modeling, so in traditional methods, position space methods of PE, you would have a grid, and then you just have an error at the size of the grid. The error is measured by that lattice spacing. But you could say, why should we settle for that? Let's again model the behavior of the system on smaller length scales by simulating a lot of them on smaller length scales and learning model that reproduces those features. Okay, and again, a lot of uses of this. This is one of the more popular and better known applications of machine learning to science and mathematics and practical ones. You know, this now gets used in weather forecasting and climate models, especially the idea of the subgrid modeling is very, I don't know if it's better, but it's very much faster. And so you can make lots of forecasts where before you can just make a few, you can get much better uncertainty estimates in the distribution of forecasts. This whole idea of fitting simulations gets used a lot. So places within particle physics, fundamental physics, this is used to optimize lattice gauge theory, sampling. Modeling in neuroscience is a big topic at Harvard here as well. This mathematical understanding of fluid dynamics is an interesting one. I'll make contact with this in the next slide. And there's an interesting program for trying to prove the existence, if they exist, of singular solutions to the Navier-Stokes equation by finding them using machine learning and then using the numerical solution and showing that there's a rigorous solution near that. And I'll talk on this slide a bit about our project in progress. We haven't pushed it through yet, but a topic which the string theorists here will know very well is the famous Calabi-Yau manifold metric, a Ritchie flat Taylor metric, usually in 6 dimensions. And Yau proved that these exist back in the 70s. Foundational, it turned out, for the subject of a string theory compactification. And then more recently, computer calculations of these metrics, because there's no analytic expressions, but numerical calculations, and then using machine learning techniques, very general, reasonably accurate numerical calculations have been possible. There's a recent work of mine with Daniel Platt and collaborators promoting this to a G2 metric. And the interesting thing here, besides the G2 metrics we're interested in, is that this is an argument which I didn't quite push it through, but could turn into a rigorous argument. Basically, Joyce and Cargianis, the mathematicians, have a theorem that, well, if you can find a harmonic one formed with no zeros on such and such a spectral Lagrangian manifold in your Calabi-Yau, then you can promote that to a 1 higher dimensional G2 manifold. And one would imagine showing that the numerical solution, which we found satisfies those conditions, in particular that it's non-vanishing, not just to some level of numerical accuracy, but strongly enough that you rigorously prove that there's some non-vanishing harmonic one form. So that's the linear, relatively easy version of this. And the current project is to try to do this for the actual existence theorem for the Calabi-Yau. So this is getting technical. Yau's theorem roughly divides into 2 parts. There's this kind of general part, which is the second part, which is say if you can show that the solution is close enough in precise sense to a Ritchie flat, then you can reformulate the equation. Ritchie flat, this is a fixed point condition, and here's a fixed point theorem to show, well, yes, there really is a fixed point somewhere near you. It must exist some Ritchie flat metric, which is exact and close to this numerical one. And then the first part in Yau's proof was then to, knowing next to nothing about the metric, show that metrics actually satisfy these conditions, and by some initial arguments you can get it something close enough. And that's famous the hard part, the a priori estimates. But our plan, which we've made some progress, is to basically take the numerical calculation and do it well enough to a priori estimates for a metric at a time, and then rigorously prove these techniques for doing verifying the numerical calculation and rigorously proving it. So that's an example of again machine learning for scientific computation directly producing rigorous results we have in mathematics. Okay, so that's one of my 4 topics. Mathematical data science is what it sounds like. You have a mathematical data set, and you're looking for patterns in the data set that might then suggest conjectures that you could hope to prove or disprove. So what is a mathematical data set? And this discussion is we again, this is a major topic in our program. This is Dupont Lee, who will get back to this work in a bit. But the point for mathematics and data science is less that, as you probably know, there are data sets out there, like there's big databases of the knot theory, the China knot census, all the knots at the 19 crossings is the famous L function in modular form database. These are resources that you can download. We could value this up for machine learning, but from a mathematical point of view, the main point that is that it should have some sort of simple definition, so that if you find something, you can precisely say, well, yes, this is what I found. So I can put in a precise statement that I could prove. And so from that point of view, we would define a mathematical, or I like this word platonic data set. There's some set of mathematical objects, such as knots. There's some function on the objects into some almost always high dimensional vector space, so properties and variants of the objects. And then there has to be some way of taking out a subset from the objects, because obviously if you're going to feed into a computer, it has to be finite, and it should be something relatively simple. It might be that there's some measure of complexity, like the number of crossings, and this one has all the knots up to 19 crossings. This has all the elliptic curves up to a conductor 500,000 and so forth. But something precise and simple. It might be that there's some precise probability distribution you sample from, but in any case, this is now the data set that you can say, well, I discovered this about this data set. I'm going to try to prove something, Okay, so that's the input to machine learning. And basically we have this set, it might be knots or something else. And now we apply F to the set and we get this crowd of points in high dimensional space. And that's what we get to the machine learning. It doesn't know any math, it's looking for patterns in that crowd of points. What kind of patterns that people found. So this is probably, at least at the moment, the most famous one is what's called the murmurations. And again, I'm just going to assume, for those of you that have seen this in number theory, there are these L functions of elliptic curves. There's based on the number of solutions for reducing the equation to any given prime p and counting the coefficients in a very simple formula in terms of the number of those solutions. And then if you do this funny thing, which wasn't really tried before, but if you try to work with this with machine learning, and fairly quickly I led to it. I begin my paper with Q1. He explains how he and collaborators were led to do this. You can average a bunch of curves over some range, like conductor n up to conductor 2n, and you average these coefficients A for a given prime index, the first prime, second prime, the third prime, and then here's dots, so we didn't do the averaging yet. Here's a bunch of these curves for blue rank 0 and red rank 1, and you see, well, you can tell the difference, rank 0, so it's up there. So there is a signal that machine learning can predict something about the rank of the curve, but then there's this kind of oscillation that when you start out, red is below, but eventually the oscillation gets off and it keeps doing that. And so they were surprised and they went around to the number of theories plus that. And they were all surprised. So this was a discovery. And there's been more recent work, not for elliptic curves, but for example, for modular forms proving, getting some idea of where do these oscillations come from. So that's a discovery of a pattern. Humans using machine learning, but clearly following this need to assemble the data in such a machine. Because they came out of our workshop at the URL. This is a similar thing of finding murmurations in the Knox form coefficients. And this part of the graph. And give you the example of interesting results found in the paradigm. This is a 4-year-old paper from Alex Davies et al. DeepMind, working with mathematicians such as Mark Lackenby, the knot theorist, and using this Regina knot census and supervised learning, they were able to identify a new relation between knot invariance, which Lackenby was able to prove. So that's an example of mathematical data science. Those are, I guess, my examples for this talk. If people want to stop me, I can say a little more. But
So are any of these proven?
well, that one was proven. It's the
That's a theorem.
that's the theorem. That one was proven.
What about the murmuration?
There's a result by I believe Nina Zabalani is here, or in math here, and she has proven a version of this for modular forms. Okay, so a third topic, constraint optimization, constraint satisfaction. This is like a core computer science topic, and you're searching for solutions to some big set of discrete constraints or conditions. And the famous, in fact, defining paradigmatic example of this is the satisfiability problem, that you're given some list of Boolean variables and variables that can either be true or false each, and some big Boolean expression like this, and you have to find an assignment of variables that makes the expression true or prove that there is no such thing. That's the SAT problem. And then this is the paradigmatic defining example for NP, class, the SAT, and proving there's no solution exists is a different class co-NP. There's not a symmetry between the things. And famously, these are hard problems. There's no general method that believed to be no general method because in polynomial time. And roughly you could say even just the brute force, try everything. Well, that's exponential time. That's easy. It's hard to do a lot better. Of course, practically better than brute force, but it's still kind of exponential. And there's a variety of count solutions, find maximize number of true clauses, generalize from Boolean variables to variables taking several values and so forth. And so there's, again, a lot of software to do this kind of thing that you can turn if your problem fits into this type of a scheme. We talked about quite a few such problems in our program. So external combinatorics in particular. So famous conjecture, I believe, Erdos, how many edges can a graph with n vertices have such that there are no 4 cycles. So if you do 3 cycles, that's easy, but 4 cycles is still an open problem. And the best results are found using methods I'll describe. When we catch that problem, we have vectors in the n-dimensional space over the field with the 3 elements, and we want to find the largest set so that no 3 are collinear. The empty hexagon number. So what's the largest number of points in the real plane in general positions, no 3 points are in a line, such that there must be some hexagon, drawing around the points, enclosing no points. Okay, so surprising, but well, no, this was proven. Okay, there's a specific number that came out of a SAS solver, which is proven to be the answer for that one. And there, again, slightly intricate problem with structure, but not obvious ways to work on it. And the computer's good at intricate problems that involve searching through many constraints. And then you can generalize. These are all defined by constraints. An example of a more general discrete problem will be find the path in a big Cayley graph. So an example of this, I've heard that recently, is this famous the Andrews Curtis conjecture, which is relevant to 4-dimensional topology, can be phrased as is such and such a Cayley graph of this infinite group connected or disconnected. So that's another of these types of things. And I won't go into, I presume the slides will be available. So there are these standard techniques, and then you can throw machine learning into the pot here. And this is a thing where machine learning helps, but typically the best solvers are not so much based on machine learning, but it's part of this, again, computational paradigms for solving problems in mathematics and mathematical science. This is an example that we worked on in the program. In fact, we recently another paper came out it's called the fun search, which is fine, and also generates functions in solving problems with language models, which I'll talk about for shortly, generate the functions. So, well, let me show you the example. So it was applied about a year ago by DeepMind and with Jordan Ellenberg and collaborators to find solutions to this CAPSAT problem. So recall this is, we have d-dimensional vectors over the field with 3 elements, and we're looking for the largest that we can find with no 3 collinear. And then a language model generated this solution. So this is a program which, given a vector, produces a real number score. And then how is it used to produce the set? Well, you just go down from the top and you add it to the set if it's allowed. You go to the next one, you check, does it violate that condition? There's only 3 in a line. If it violates, you throw it out. If it doesn't violate, you add it to the set and keep moving down the list. And so you've reduced this generation defining the set to produce a function of vectors. And then this Python program producing this record-setting thing for the 8-dimensional case was generated by, I believe, a Google language model. This is a DeepMind project, which was programmed as prompted. You play with this kind of thing. You give it a list of the programs which of that type, which are candidate solutions to the problem. They generate their functions of a vector and they produce the score, the ranking. And then you give it a list of those, and then you say, make me another program like that. And it does that. And then you evaluate the new program along with the others, and you keep the top one. So it's sort of like the evolutionary algorithm of older AI type of work, but in this sort of, taking a population of programs and using it to generate into smaller programs. So that's an interesting machine learning based combinatorial optimization approach. This is again a paper that just came out under does this for quite a few other problems. Okay, so that's the third, and now the fourth of my review topics. Again, I'm trying to show you what I think are the most successful paradigms as of 2025 is this international theorem proving. And again, very long-standing idea, which was made precise in the early 20th century, this idea that proof can be reduced to formalism, to just checking, writing out the statements in a formal language and applying a finite list of rules of deduction to that to see if you can reduce it to a trivial statement. Famous early attempts to do this, like contributing Mathematica, showed that this can be very long in practice. The proof of 1 + 1 = 2 was supposed to be 10 pages long. And that problem was eventually solved. And it's very analogous to the problems that every computer program or software engineer faces, that programs are just long and complicated. So we have all these tools. We have computer science tools for structuring these programs and producing libraries and building on past work. And then there's also essential developments in mathematical logic and what the framework that gets used. You could use set theory, but what gets used in all the practical systems is type theory and lean, which I'll talk a bit more about dependent type theory. And these also are simplifying the problem quite a bit. And so there are a few flagship complicated, hard theorems that have been verified in this way. The four-color theorem is not just a computational check of many graphs, but that check has actually been verified by one of the in Coq. This was done in the mid-2000s in France. The Feit-Thompson theorem from group theory. Thomas Hale's famous proof of the Kepler problem, the packing of spheres in 3 dimensions was verified. The Embler verified Roy Tucker's proof of that the Lorentz system is Smith's 14th problem is sometimes called as an example of this. And so the system which has attracted the most attention, and I think used right now, is called a lean 4-to-4 version. And there's a sizable community that probably many of you read articles in Quanta and elsewhere, hundreds of mathematicians developing this, building up its library, which at this point covers pretty much the undergraduate math curriculum on some topics. Some recent accomplishments you can read. Probably the most famous is this verification of Peter Schultz's foundational lemma in his liquid mathematics program with Dustin Clausen. So this was, I guess, years ago, developed this quite abstract framework and proven the foundational lemma, which he was, proof, but it was a proof which was sufficiently non-intuitive that he wanted to check. And so he reached out to this community and asked, well, you claim to be able to check theorems with a computer, try this one. And so they took it up, and within 3 months, they were able to address the point that he was most worried about, assuming this and this are true, we can then prove that. And within about 1.5 years, a group of about 10 people, I guess, working part-time, were able to fully prove from the formulate, to the logical foundations up and verify that this piece of work. So that's possibly the first example of one of these computer theorem provers addressing and solving a problem which the actual mathematician had posed and really wanted to know, was it true at the time he was working on it. So that's a milestone. And again, many other important, interesting demonstrations of the power of this. Many even more ambitious. Kevin Buzzer with Imperial has this very ambitious program to prove some good part of the Fermat, Law's proof of Fermat. But it's honest. The honest statement at this point is that this is a hard thing to learn. This is why hundreds of people are using it, not thousands. It takes a year of study used to be professional at all. Here are,
sorry, I have a naive question. So for this technique, the point that you have to interpret the existing proofs
Uh,
into the language?
Well, that's
and-
why you could do it. You could develop a new proof too, but it's right, the human is making the proof and the computer verifies. And I'll just give a couple of examples, maybe will help. So there's a statement in the proof of the Pythagorean theorem. Okay, so it's called that. And this is it's not that hard to think. And the notation is a little funny, but the distance from P1 to P3 squared equals the distance from P1 to P2 squared plus the distance from P2 to P3 squared. If it's a right angle. And then here's the proof. And then the generalization to the case of, more general angle. And again, just to simplify a bit, these statements of the theorems and the definitions are actually pretty accessible if you go and look at these things. And then these proofs are really, I won't say gobbledygook, but I just say, they're very computer-raised. They use these somewhat, there's a system, but again, there's clearly a lot of knowledge and structure involved in writing this proof, which are the explicit manipulations that you would use to rearrange the formulas and bring in axioms and so forth to prove it. That I think you would hope that the eventual solution to theorem proving doesn't require you to write things like that or read them. And one solution that would be that AI could write those proofs. Why not? And this is another subject that's a very long, it's a core topic in computer science, formal methods. There's a fairly successful, the most successful approach right now is something called a sledgehammer, which exists for a system called the Isabel competing system, which has other disadvantages, but in this way it's better. There's a technique where, so the higher order logic, which you need to formulate pretty general mathematics, allows you to quantify anything, functions. And this is just very, very general. A much simpler problem is you have quantification in variables, but you can only quantify over a set, so not functions. And you can express, an interesting fraction of mathematics in those terms, but you can't, for example, the real numbers are, talking about the sequence, infinite sequences or rationals or some other way of constructing. And so that's not a thing you can express in first order logic. You have to quantify over that sequence. And on the other hand, based on mathematical logic, turns out if you have a list of all of the lemmas that you want to bring in and the statements you're trying to prove, you can actually find a kind of informal translation that's into first order logic, where you introduce all these kind of extra symbols to represent all the possible unknowns that could appear in the problem. And then first order logic proving is actually a much easier computational problem. And this exists for Isabel, and the proofs are rather easier to read. And this is in the process of being developed for Lean. So it's both something that will exist probably in the next year or two. And it shows that these kinds of difficulties are not inherent to the concept. It's just the level of automation of this Lean directive is not yet satisfactory. Okay, so that's kind of this computer science approach. And then people are very much trying to use machine learning and AI to do this as well. So you could treat it as a problem in reinforcement learning. Say it's the steps in making the proof are like the moves in a game of solitaire. And if you prove it, you win. And so we're going to use AlphaZero type technology, and that's been tried. That has some value. The more recent work all combines reinforcement learning and the language models. Okay, so now I'll start talking about, so those are my four paradigms. And so the language model, okay, so
So the prover's goal of the prover is to prove.
It's a verified.
Okay.
This is a verified, so the proof really is kind of spelled out. Let's not try to read this in detail, but it's things like, complete the square, move this term to that side, bring in this lambda, and do it to that, and that kind of thing. And then it verifies the proof.
Question.
Yeah.
So I've used an interface to Coq that can accept commands using natural language.
Yeah.
Is it going to be the case that that'll be superseded for Lean by AI?
That's exactly what we're getting now into in the talk. Exactly. That's right. So that's what we would like. And so here's again, very, very lightning review of the language model, which I'm sure you've all seen on this topic. And so we have these statistical language models, which you're given a string of words or tokens, and it predicts a probability distribution that the next word will follow. There's a very nice set of models called the transformer, which seems to be what is very good at exactly that type of task. And you train it on just huge corpus of text, in some sense, everything you can scrape from the internet, you just predict go through one word at a time and predict the next word. Now, this is, this word appears, there's a sample for the empirical probability distribution. And it just keeps doing that. And then the surprise, of course, is that not only does it generate plausible text, it generates kind of sensible, in fact, more and more sensible text that can involve solutions to questions that you've asked, answers to questions, solutions to problems and so forth. And so this is, clearly the most significant advance of AI in recent years. And so you no doubt play with ChatGPT, and you've probably very likely heard about the problems with ChatGPT, that's type of technology as of a year or two ago, the hallucinations, the inability to kind of carry out long arguments. And quite a bit of progress is being made on this. It was like as we speak still, like the big research topic in the AI labs to get some systems that can do what you might call reasoning, solve problems that require longer chains of argument, that are unforgiving of mistakes, that might require making a hypothesis and then falsifying and taking it back and trying something else. So these various abilities, and there's been a lot of progress. I've just described to you a couple of the conceptual ways that people think about it. So this analogy to the dual process theory, the system 1 and system 2 of Kahneman and Tversky, that human thought was modeled by a system 1 that kind of immediately responds to a question or recognizes an image or something. And that's in some sense analogous to what the language model does. It immediately produces the next word. And then if it's a problem that you have to step back and make a plan or think or hypothesize, then the system 2 comes in. And that requires conscious effort. That feels like effort. All sorts of experiments in psychology distinguishing these things within human thought. And so the goal from this point of view was to say the language model as of a year or two ago had the system 1. Now we got to give it the system 2. So we had some success. Another concept that people talk about is this trade-off between training time and inference time. And it's basically just the idea that instead of making it just generate the next word, we give it more time to do something more to evaluate these next words, and perhaps it'll take something back if it has to, or perhaps generate a plausible line of arguments, and then reflect on it and then continue in some other line because it decided that so forth. And this can also be quantified, just kind of a trade-off. Okay, so a lot of this work is proprietary. This is like the competitive edge of many of these labs. The famous DeepSeek has actually been more forthcoming in their papers than OpenAI. It's clear both in DeepSeek's work and more generally that you have to use reinforcement learning, because if your goal is to get the model to produce correct solutions to problems, well, you can't judge it on a word-by-word basis. You have to look at the solution and judge whether it's correct. And that's this definition of reinforcement learning, where you get a reward later and then you have to feed it back and try to figure out what parts of which of the various actions that I took contributed to the success or the failure of the whole thing. And so that's the reinforcement learning technology. But then the signal can be based on a variety of things. There's this famous reinforcement learning by human feedback, where many companies would give like A/B example of this model. Here's two answers, which one is better? Humans would sit and judge this one was better, and then they would train another model to generalize that into a training signal. There's what's called process reward, where you don't necessarily check the thing, but you say, well, at least it looks like a sensible argument. It's got the first statement, the second statement depends on the first, and so forth. That's helpful. And then, of course, if you're generating mathematical proofs like this lean language, you could feed it into the lean verifier and very directly get the signal of yes, this proof checks. This is a correct proof. So that's kind of the gold standard, and that's one reason why the AI researchers are so interested in math as a domain. Okay, so this is now an example of the OpenAI deep research that came out, I don't know, 10 months ago, maybe. And this is the first of these language model systems. At lunch, we were agreeing that a year or two ago, you type a literature search, a kind of a question of interest. So here I'm asking it, tell me something about the experimental search for supersymmetry. What could happen if we had 100 TeV profiler? What does string theory have to say about this? And a year or two ago, this wouldn't have been a total waste of time, but I would do much better off finding a review article. But now this thing produces a pretty decent answer. So they're, excerpting, fairly long, it took about 10 minutes. And, I wouldn't say, I even checked it 100%, but it's a topic I know something about, and a lot of it is clearly correct, and it's producing the right references. And it's a very useful starting point for good research. This has become a go-to thing for me if I'm looking for results, literature search for recent papers, what are all the papers that.
What do you mean by correct here?
Well, of course, I know something about this literature, and so I'm comparing with what do I know about the literature. Obviously, this one's
So
okay.
correct means that it reflects the.
Yeah, exactly, yes. That's right, that's right. It's not really claim, it's not, they don't claim it's creative. It's doing the literature search and synthesis of a summary.
How discriminating is it about the literature?
Well, you can try it. That's my basic answer to you. You try it in something where the literature is much more controversial.
Training on papers that are obviously wrong.
I encourage you, I would like to hear what you say about it, because
The
indeed.
fact that it mentions the CMSSM is a reason to ignore it. It's an excellent reason to ignore it.
Okay, so anyways,
Mike, what are those grade things there? Are they?
those are reference citations, exactly. You can click on things and get the papers that it's drawing stuff out of. No, it's not 100% for sure, but again, it's a big step forward from where we were a year ago. Okay, this is an example of auto formalization. So here's a simple problem, and then here's how you could formalize it in lane. And then here's the progress of systems doing this by whatever means, one of these benchmarks. So here's 2021, when this was posed, something like 20% was able to do. And then, people in computer science, they compete to make systems to do better on the benchmarks. These are the ones that didn't do better. State of the art so far, and it's gotten up to above 60%. So there's a steady progress, and that's how people work out these things. And so that's an example of auto formalization, turning informal math into formal math.
Sorry, this is like the correct rate.
Yeah, so this main F2F is a set of several hundred problems just like this, and then this is the fraction, the percentage that were correctly done. Okay, here's another, this is the alpha geometry and alpha proofs. Alpha proof is from last summer, and alpha geometry before. So these are medal winning level performance of IM model questions. I'm hoping we're going to get a talk from the lead author at Alpha. If you follow these things, you'll know there's still no paper on it. And as we still no paper, I don't know, but he is scheduled to speak for us on March 26th. This is an example from this. Let me move on now. This is the state of the art. So now we've come back to this graph illustrating the exponential progress. And so what are these things? Okay, well, the red dots, okay, well, blue dots, that's the ImageNet. So that's one of the sameness benchmarks. And then this is a index just based on that one, where it's basically every time somebody does better, you take the fractional improvement, the ratio of the open -1, and you add it, and you just keep raising up. And then it's roughly comparable to like a logistic function of that thing, sort of an exponential relation in the middle of the curve. And then using many hundreds of benchmarks, so the place where this one came from, but hundreds and hundreds of these benchmarks. So my collaborator Sergey Verstov, and I developed an index which combines many benchmarks and measures that tracks the whole progress of the field of AI, and that's what these red dots are. And you see this pretty steady exponential growth, okay, in this performance measure based on how does it improve those folks, 50% to 95% would be like 5% error, that'd be like a factor of 10 in performance. And by that measure, it's been growing exponentially since about 2010, when these benchmarks start, by a factor of about doubling every 2.5, maybe 3 years. Okay, so that's the red dots. These lines are more traditional measures of patents and papers. So what economists might have in the past looked at to measure progress in the field. And this green one, okay, what's this green one? The green one is computer chess. And so computer chess, of course, we see all this progress. Will these computers AI get better and better. Well, if they keep progressing, I say that line is going to keep going up. And at some point, they must get better. So how can we think about that? Well, here's a field that this already happened. It's happened back in the 90s, 1994. Computers were, and I think I started saying comparable to the answers by 2004, really superhuman. There is this pretty objective rating system, the ELA system, and it has a simple mathematical definition. It's basically probabilistic. You compare two players, and you want to characterize the probability with which player one will beat player two. And basically, a 400-point advantage in this ELA system would translate into a times 10 a sigma improvement in the probability of the win. So we have this fairly objective measure, and then people have been doing this for a long time. So we have this fairly good idea of how many people have these various levels of ability. So this is the 2015 Federation, International Federation of Chess listing, which I forgot Wikipedia, but it is their listing. And so starting at 2,200 is somebody that might be playing in tournaments, might be ready to, win, to pass the criteria to be a master, which is a sort of a separate, thing based on winning tournaments. 5,000 players in 2015 at that level, all the way up to this 2,800 scale, the very best players for them at 2015. And so these intermediate to gradations in a 600-point range. Okay. So now what this green line is quantifying that for the computers, and there's a number of people, in particular, is the Swedish Chess Computer Association, the SSDF, and they've been ranking chess engines by playing them against each other since the 80s. And so they can very steadily track that's what these green dots are. And it's really very steady. It's really about the same slope as these AI lines. This is before deep learning. We're not necessarily AI programs at all. These were just whatever the best chess program was at the time running on a PC. And again, doubling in performance. And so ELO, this is linear in ELO because the translation is, as I said, 400 points of ELO is like times 10 in performance. So
Looks like there was a discontinuity in.
Yeah.
What is that?
We didn't track it down, but I think they switched.
Then it got worse.
They switched PC at that point. Yeah. I
So
mean,
it's PC.
yeah, because they every few years they upgrade their PC. They say it in their site. We didn't try to we just took their numbers at face value, and the overall lesson is that there's this really steady improvement, about 54 ELO points per year, with the slope matching, and there is this canonical identification between the ELO and the benchmark performance, which are at the same slope, and so it leads to the obvious kind of conjecture that progress in AI doing other things can follow the same progression. And that if a computer is able to somehow match the level of performance, whatever a candidate master in chess translates into some other task, let's say doing research in math or physics, then roughly every 2 years, it will progress down the scale. And after 12 years, you'll be at the level of the top human. So that's the picture that I would have is that it's much more quantitative than what I was thinking. This was rough analogy to the history of chess. I think that in many people's mind, and I think this idea of the exponential scaling is in many people's mind, but you can really be much more specific about it. And so this is kind of what I'm going to advocate is that when Sam Altman and Gary was talking about AGI, they're not talking about this, they're talking about this. We're talking about the system, which is kind of a useful assistant, that at least it's worth giving your math problem to, and sometimes it will be able to do useful stuff for you, but it's by no means superhuman. And that, I do believe, based on the previous discussion and everything I thought could come in 2 or 3 years, and now we have this type of progression ahead of it.
Question?
Yeah.
Does ELO basically track compute? Is it?
Well, I mean, again, this is, basically, yes, there's another graph in the paper which demonstrates the exponential growth of computing, which is not just Moore's law, because there's also how much do people spend on computers. And for these people, again, they're just putting in PCs, so they're not, but I mean, roughly, yes. I mean, in the same sense that these things track compute, in this, logarithmic way, since ELO is linear on this scale. Okay, so what does this mean? You know, what kind of, I say, you know, maybe in 2 or 3 years, the core AGI for us will be this mathematical research assistant. So what is the mathematical research assistant? And again, it's one of these ideas that people have been throwing around for quite a while. I looked for Jerry Sussman, one of the pioneers of AI, and in the 80s, he had this idea of the dynamicist workbench. He was very into celestial dynamics with Jack Wisdom and others. And, so this would be something which helped to run and interpret computer experiments in the ODEs of, say, celestial mechanics. And at that time, it was, you could start out of ideas, just, you know, a huge amount of programming to get that far, but now it starts to come within reach. So there is this vision of, well, we'll talk to it when we talk to ChatGPT or summary system that deep research. And that is definitely a valid and very valuable function of an assistant, but there are many other functions. And so assisting with coding is one which, again, if you follow this, try it out all this stuff, you see how this is advancing. And so that's clearly something of value in many forms of research. Direct analog of coding is exactly writing out these formal proofs and reading other languages and then going the other direction, translating formal into informal. And so that's a thing which, yeah, it's very, there hasn't been a 99% success yet, but there's like this, 60% level of success now. It's very plausible to think that that will already be on a track that one can predict the progress. So people, I think, quite reasonably predict that within less than 5 years, the system will be good at taking a natural language outline, detailed, outline of the proof and turning it into a link. Yeah, the language model is not good at everything. It's not good at checking detailed calculations and arguments. So even, the super smart language model might as well use ITP for its own purposes. Okay, but that's the logic part of it, which we understand better. And then there's many other aspects of, research of writing and math and physics, which have not been formalized. And here's a few various people I talked to that try to develop together, because it's not the cutting edge. What could the assistant do for us? How should we formulate that? How should we train a model or otherwise, produce a benchmark to get it to do that? So workflows, sequences of operations, like in this example of the dynamics workbench, here's my equation, initial conditions. Now I have all the methods available to you and so forth. I want to see how it behaves over the next 10 years. I want to get some sort of qualitative picture of the phase and so forth. So it's possible to state, what's the general goal, but there's so many variations in the problems and how you might do it, that it's not a, it's more than just a programming problem of carrying out an algorithm, but it's really less than AGI, commonly understood. It's be a very valuable thing that the system can do. Again, you look at texts and papers, and you get other ideas for levels on which the assistant can help you. What are motivations? Examples and counterexamples are typically particular definitions, and in that sense, they're just definitions, but they're very well motivated because they falsify this interesting claim, or they, for some other reason, difficulty estimates, intuitive actions. And again, if you delve into the computer science analogs, there's a lot of ways of thinking about these things that are just in terms of natural language. Sometimes it's useful to formalize. Okay, so I think it's common. And again, I don't think the reliability, I think this is a limiting point, that things do make mistakes. You can only, make an argument at length 1/epsilon if you're so that's really a limiting factor. You need things that you don't want it to do all your calculations. You should be able to use tools and programs. This is clearly common. This is an example of a recent Google AI co-scientist. This is in biomedical. Different problems come to the fore, especially huge literature so difficulties of doing experiments. But it's a real research project. That's something real. Similar, trying to flesh out again. I hesitate to spend a lot of time on the details of fleshing this out, because this is now, what one is trying to figure out, and because AI is changing, making a lot of things easier than they were before, and making some other things not easier than they were before, perhaps work which is not really worth doing. So that's kind of the challenge of today. Where do these new capabilities? How do you best leverage them to produce the biggest, benefit or, assistance to, how we might do our research. Okay, so suppose you want to push back on this. Well, the point that I like to push back on is that, and this might seem a little contradictory, I would maintain that although, it would be very reasonable to ask a computer to start doing research and discovering something, the history of Mars is encouraging that that computers have.
What about the murmurations?
Because that was a human using the computer, right? The human set up the data and then used the data science.
The human
said,
had to think
here was a
about
discovery.
looking at this
So
particular
this
combination.
word autonomous, so
or
definitely the
coefficients.
whole talk has been about helping people to make discoveries, but autonomous would have to mean that it sets the thing up and then it points and, at least, like number 1 or 2 on this list is, look at this, this is really interesting. And that's the interesting thing. It's not a human going down a list of 100 things and saying, yeah. So I think that's a fair statement at the moment. And there's all sorts of interesting tests that you can make which fall short and might be easier than having a computer literally discover mathematics, which is new as a human, like an interesting thought experiment at this point. But one that I think one could work on would be give the computer knowledge of human mathematicians around the year 1800. So we know something about the significant discoveries after that, famously Galois, famously Dedekind. And so would the computer be able to make these discoveries? And I think it's a pretty fair bet that none of the systems now could, but is there some barrier? Is there some reason why it could never do that? And I think the answer is no. It's just, again, beyond what's been done so far. So I have another talk that I've given. It's online, the recording of this one about this whole topic. Again, there's a few exploratory works, but it's something which has not been really received the due. But I think it's just now coming within range. I'll mention my friend David McAllister, who's that was for quite a while from the more modern AI perspective. And so yes, it's a valid objection to say that, unlike most of what I'm saying, we are kind of saying that the computer's going from near zero ability to potentially superhuman ability in 12 years. But on the one hand, that sounds kind of crazy. On the other hand, of course, there are all sorts of really weird, crazy things where it did that. The ability to write poems about the proof that the prime, there's an infinite number of prime numbers, and probably all of you have seen that kind of thing come out of ChatGPT. Well, I'm not going to say that's an analogy. I'm just saying that something can come from near zero level. If it depends on a sufficiently rich and complex set of skills being combined, then it can seem like zero before you get those skills together. And what I would also say, again, this is not the frontiers, that it would be very plausible to hypothesize that the architectures we have now, but even more with the training data that we have now, but just training a model on question, answer, question, answer, question, answer, or is not going to be enough. You clearly have to understand something much more deeply to make a discovery and realize why it's making a discovery. But I don't think that's an argument that it can't happen. It's an argument that you need a different training set, different ways to get the computer to do that. Okay, so my conclusions. Machine learning, I surveyed these various paradigms of the use of machine learning and mostly math and some physics research and useful evolutionary progress, and you can certainly compare that. AlphaFold 2, that was revolutionary. Revolution is possible, has not happened. Interactive theorem research is lead. Again, very promising. Clearly, probably a central part of the story of the computerization of mathematics. But still, the foundations are there, but it's hard to use. It's not like mathematics or Sage Math, where you can just fire it up and try it out and get useful stuff. Okay, but nevertheless, despite this kind of qualified 2 cheers, we're still on this exponential, and those reasons that have been raised to expect the exponential to break down. Well, Moore's law already did break down in some sense, but people pay much more to build their computers now, and they invest in them. It's true, we did run out of training data on the internet, but almost all the data I talked about in this talk is synthetic data that was produced by the computers themselves. There's no a priori limit on synthetic data. These big data centers require lots of energy. Ultimately going to clearly be a limit, but it's not going to be a limit in 2 years. So, and I would interpret this prediction that AGI is coming in the next 2 or 3 years the way I said, that we will have these kind of useful math assistance, where it is a thing that, many of you will be tempted to use as part of your work, not like it solves all the problems, but it's just useful. And then I would make the analogy to compare that with that. I mean, candidate master, that's a point which could be discussed, of course, that's a little bit subjective at this point, but I think it's a plausible analogy that what people talk about as AGI and exhibit in other fields, that the analogy is this kind of low level of chess, but skill and mastership, and then we're on this trajectory where 5 or so years after that, the AIs will be comparable to the top researchers around the world, and 5 years later among the greatest human mathematicians. And so I think this type of argument convinces me quite a bit more than I was before I had these thoughts. And I think there's a lot to be said about how this will affect society as a whole and how we do scientific research. But I think in the long, not too distant long run, but the 10, 20, 30 months, the response to this is not to despair, but to say, well, we really should be much more ambitious. We're going to have these vastly better tools and abilities than we had before, and we should find the big problems that we really want to solve and start to put more attention into those, because they will start to come within reach. Of course, they'll be great dangers, but great opportunities. So I'll start there.
Thanks, Mike, for the wonderful talk. Any questions? Yes.
So a tremendous amount of mathematics is in paper journals. Is there any organized effort to get journals scanned and digitally available?
Well, I mean, you might know more about that than me. I mean, some journals are scanned. And they will be with scanning.
A lot of them are not.
I mean, I agree. I agree. That's a motivation for just what you said.
But are there copyright issues with using this stuff as data for AI systems?
Yes.
And what's happening in that regard?
Well, I think the big case is the big guns, like the New York Times and these people, they think until that gets settled, everything will be kind of uncertain. I mean, of course, math, it doesn't have the same commercial value, so it's much more easy to imagine. Entering into agreements with specific publishers, and solving the problem more easily.
Autonomous mathematics means you turn on the computer and say, do something interesting.
Yeah. Exactly. That's right. Not like autonomous driving. There's nobody behind it.
I have the following question. There is an obvious shortcoming of machine learning, namely it searches patterns in the mathematical structures imposed by the algorithm.
Right.
In this particular case, these are so-called sigmoid. In other words, it's glorified curve fitting in space using smooth functions. And in case, for example, if you would feed to machine learning all the knowledge about classical physics, would never derive quantum physics.
Right.
The same thing about astronomy, would never derive relativity, because there are some very simple imposed patterns. So this obvious shortcoming could be overcome by combining AI with ML. So AI would be capable of changing and suggesting the spaces and the mathematical structures used in ML. And that is, I haven't seen that yet.
Well, no, I think that's in a lot of people's mind. That's sort of the subtext of the whole talk. I presented these first half, which was largely methods coming out of ML. And then when I say, how will AI help us do these things? Not all, but again, a good part of the answer is to help us do this ML stuff much more efficiently and eventually do it themselves. And again, the AI can use an ML tool. So I agree with what you said, and I think it is part of people's thinking.
So a lot of people in this room have made amazing discoveries using path integrals. What would your mathematical assistant?
Well, right, okay, yeah, that's right. Do you need formal?
Rigorous mathematician is going to come back
Well,
and say, well, it's not all the fun.
that's an interesting question. Now, no, I mean, again, the first comment I would make is that, again, if you go back like my 5-year iteration of talks, I following, everybody, established practice, I said all the math has to be formalized for the computer to really deal with it in some way. And now we have these language models that do not require that and do work with informal things as well. And so there is some ability to reason informally, not to do a path integral to think about it, but it's there. And so that's one part of the answer, is that we see that reasoning is more general. AI doesn't have to be based literally on fundamentals. Of course, another style of answer would be the similar fundamental, but be formalized.
Well, I was
And,
expecting that, so then it's
I mean,
gonna be.
that's a worthy goal in its own right. Another answer would be to say, well, what's the difference between the mathematician concept of formalizing and the physics concept of how they think about things? Well, they're both making precise logical arguments, just the mathematician reduced it down to a ZFC. It's a very small number of answers. Physics cannot. Maybe physics has 1,000 axioms in the back of it, you know. But still, it's maybe more analogous than one usually thinks. So it's an interesting topic for discussion.
Any other questions for Mike? All right, if not, let's thank him again.